Well, welcome back, mathletes. This is our second video in our discussion of restricted domains and piecewise functions. This one's going to focus more on piecewise functions. Piecewise functions are basically functions with several domain restrictions, and you have a different rule for each restriction. So um, I could keep explaining it verbally, but I think it's probably going to be best if we see an example right now. So a piecewise function is basically a function that's described one piece at a time. So here's an example of how you might see this. Right? So let's say I have f of x is equal to, and because it's more than one rule, we actually join them with these large set brackets, and we list each rule across here horizontally. So let's say this function is equal to 2 when x is less than or equal to 0, and it's equal to -1 when x is greater than 0. Okay, so basically what it's telling you is what the value is at each one of these, in each one of these areas. So I have an area where x is less than or equal to 0, and then I have an area where x is greater than 0. And this is just telling me what the y values are in those places. So if I'm going to graph this, actually, let's start by evaluating a couple things. Let's say if we wanted to evaluate this. Um, let's say we want f of 2, f of 4, f of -1, and f of -10. So let's see how these things play out. Let's look at f of 2 first. So the x value is 2, and so what we need to do is look at these two rules here, right? This one, and see which one 2 falls into. And since it falls into the second one, 2 is greater than 0, that means this function is equal to -1. If I plug in at 4, well, 4 is greater than 0, so we're still using the same rule. The function value is -1. Now, if I plug in -1, let's see here, f of -1, -1 is less than 0. So that means it follows this rule, which means that this is equal to 2. If I plug in -10, it's the same business. -10 is less than 0, so that means it's this second rule here, and the function value is 2. So there's only two function values that you can have. Everything else is what, everything else just depends on what you're plugging in. Now, if I'm going to graph this thing, I know I have a boundary point at 0. And I know that because both of these include zeros. Right up here, when I look up here, those are both zeros. So what that means is that there is, ooh, that's a little thicker than I wanted, but okay. There's a boundary right here. And so we need to be aware of it. That's where it changes from one rule to the other. So when x is less than 0 on the left-hand side, this function is equal to 2. So if 2 is right here, that means that this function value is a constant. It's at 2 the whole time. And at 0 itself, when I plug in 0, 0 is less than or equal to 0, so it still follows that 2 rule. So you darken the spot to make sure it's clear that that value is included there. Now, when x is greater than 0, that does not include the y-axis because that's where x is equal to 0. So it's equal to -1 all the way this way. And we want to indicate that it does not include the point here at 0. And so what we do is we put an open circle there. And so we end up with a graph that looks like this, minus the red marks. Right? The red marks are just there to mark my boundary for myself. The actual graph of this thing would look like this, right? With no dotted line in here at all, right? That dotted line is just scaffolding at this point. Okay, so let's go ahead and look at the next example here. So let's say that the piecewise function I'm given this time is g of x is equal to 1/2 when x is, let's see, are those included? Yeah. X is between 1 and 5, and it's equal to 0 otherwise. Now, the otherwise basically says that if it's not between 1 and 5, then it's otherwise. Basically, it's anything that's not in the interval above. So that is something that gets pointed out every so often. So if I look at a few of these values, let's say I want to compute g of 2. Well, 2 falls between 1 and 5, so that means it's equal to 1/2. But let's say I want g of -2, right? -2 does not fall in that interval right there. And so that means it falls in the otherwise category, which means it's equal to 0. So anything that's inside that interval, it's equal to 1/2, and then everything else has been zeroed out. So if we graph this now, we have two boundary points. We have a boundary at 1, right? And then we have a boundary at 5. I'll mark this in here shortly. Right? So this is 1, this is 5. Now, if I look at this, I'm going to go ahead and put this in too. So there's my 1/2. Starting at 1 and equal to 1, this function value is equal to 1/2. And so that means I have a point right here. Now, that value doesn't change. That y value is always 1/2, which means that it's going horizontally straight across here, all the way across to 5. And looking at this says equal to on the 5, so that's also a closed gap, right? But it's also 0 otherwise, which means I have to put an open circle here and go that way on the x-axis, and an open circle here and go this way on the x-axis. Maybe I should just thicken that up a little bit. Yeah, maybe that'll work. Right? And so the function ends up looking like this. Right? We have open circles here where this stuff starts, and it's just this broken off piece that's been lifted up. Right? And that's part of the reason they call it piecewise, is because it's just kind of chunked together. All right. So let's go ahead and look at another one here. Sometimes these piecewise functions are defined discretely, right? So sometimes you end up with things that look like this. Oops, wrong one. Let's say this is equal to -2 when x is equal to 1, 2, or 3, and it's equal to 0 otherwise. Now what this means is that this thing only carries values that aren't 0 at 1, 2, and 3. And when x is 1, 2, or 3, the y value is -2. Everywhere else, no matter what the x value is, the y value is going to be 0. So you can evaluate a few of these, right? H of 2, right? 2 is on this list, so that means it's equal to -2. H of 2.1 is going to be 0 because 2.1 isn't on the list, right? So only things on the list get a value of -2. And so what that ends up meaning when you graph it is that at 1, 2, and 3, I have a value of -2. So I got 1, 2, 3. Boy, those aren't evenly spaced, but we'll pretend they are. Everywhere else, this thing is equal to 0. So what that means is that I have a horizontal line. I come up on 1, but there's a hole here at 1. There's a hole here at 2 and a hole here at 3 because those values are down here. So this function actually looks this way. right? It's really kind of a bizarre looking thing. And those open circles right here are actually holes in the graph, right? That hole has been removed and put down here at -2. Okay, now let's look at the last example here. Now, okay, so our last example here is going to be a function that's defined with 3 different rules. So we have p of x is equal to 5 when x is less than 1. P of x is equal to 2 if x falls between 1 and 3 inclusively. And I say inclusively because it includes the endpoints. And it's equal to -1 when x is greater than 3. Now, you could plug in a few values, figure out, let's see here. Let's say I wanted f of -2, right? And I look at this. I have to look down my rules here. And if I look down my rules, I see that it falls under the category of the first rule. -2 is less than 1. And so that means the function value is 5, right? Anything that has an x value less than 1 has a function value of 5, period. Up here, if I pick something in the interval from 1 to 3, let's say I take 1.5, right? 1.5 falls between 1 and 3, so that means that the function value here is 2. If I pick something like f of 50, well, 50 is greater than 3, so that's in that third category, which means that this is equal to -1, right? And so basically, what the function value is depends entirely on which interval you fall into. Now, if I'm going to graph this thing, I have several boundary areas. So it looks like I have a boundary at 1. So let's put that in. Let's say let's just go ahead and mark that lightly there. And that value is at 1. And then I have another boundary at 3. Let's say 3 is right here, right? And that boundary is at 3. And then the last area says it's just greater than 3. So it looks like we have it broken up into our 3 areas now. And the way this ends up playing out is that if I'm less than 1, and notice it's not less than or equal to, so this needs to have an open circle at the end, but it's a value of 5. So here at 5, I have all of these values up to my boundary point, and then I have a circle at the boundary point. Okay, now the second part, it's equal to 2 when x is between 1 and 3 inclusively. And so if 2, well, maybe 2 is a little higher than that, I don't know. That means that for this particular boundary, we need to have closed values on the endpoints, right? And then we have to look at our third category. The third category is when it's greater than 3, not equal to 3, just greater than 3. And so it's equal to -1 when x is greater than 3, right? And so we have this function defined in 3 areas. So once you define your areas, it's just a matter of picking which function value you have, right? So this area, I'll call this area 1, follows this. Oop, that's a 2. Let's try that again. Right? This is my area 1. Area 2 is this middle one, and that follows this rule. Area 3 is this last one, and that follows this rule. So everything is connected. All right. So that concludes the examples here. And yeah, so that should get you through the homework and whatever you need to get through. And so until next time, keep your wits and your pencils sharp.